When an object is moving through the air and the only force acting on it is gravity, we say that the object is in free fall. Now, it doesn't mean that the object necessarily is falling. It could be something that has been thrown straight up, straight across horizontally, or even at an angle. But if the only force acting on the object is gravity, we say the object is in free fall, and this would be the force diagram representing its motion, or at least the change in its motion. You can't really tell, again, just from this diagram, what the hammer is doing, only that the force of gravity is the only force acting. But that's actually quite a bit. If the force of gravity is the only force acting, then that means that we can take Newton's second law and we can say that the gravitational force divided by the mass should tell us the acceleration of this object. The gravitational force, of course, is the mass of the object times little g. And what we see then is that no matter what the mass of our object is, the hammer or whatever it happens to be, the mass cancels out within this formula, and the acceleration of the object will equal the value of little g. Now, we have labeled little g in the past as newtons per kilogram, and that is still true. That is the way that we can determine something's weight or the force of gravity based on its mass. But if that force is the only thing acting, then that number, that 10 or 9.8, also tells us the acceleration of the object. It describes how its motion is changing. And because a newton is defined as a kilogram times a meter per second squared, the units for g can now be stated as meters per second squared when we are using this number as an acceleration. That's really the best way to kind of distinguish between those two values of 10. Let's now, though, think about a hammer that has been dropped and is falling in the traditional sense that we might think about falling. If it's dropped, then its initial velocity is 0. After it's been falling for a second, it's gradually been speeding up. And if we were to look at the split second when the stopwatch hit 1 second, we would find that the speed would be 10 meters per second. That's really what 10 meters per second squared as the acceleration means, is that it speeds up by 10 meters per second every second. So after 2 seconds, it would be moving 20 meters per second. After 3, 30 meters per second, 40 meters per second. And notice how the distance that it travels keeps getting bigger and bigger. Because it's accelerating, it's going to travel a greater distance during each interval of time. Now we have a value that we can use in some problem solving. Let's take a look at a problem and see how this can be applied. So if we have a situation where we have a hammer or some other object and it's in the air and we can detect that there's no other force at that moment acting on it, then we can use these old kinematics formulas but involve this new idea that the acceleration is going to be 10 meters per second squared. Let's go through a few examples here. It might help to list off some of the things that were given in the problem so that we can see which formula is going to make more sense. In this case, we should see that the time is known and the hammer's speed at the end, the v, not the v sub 0, but the v, are unknown. There is unknown. Okay, and then there's some hidden information. The fact that the hammer was dropped and the fact that it's in the air, not touching anything, gives us two pieces of information. The dropped part tells us that v sub 0 is 0. It started from rest. And the fact that it's in the air, that its motion is happening in the air, tells us that the acceleration is only due to gravity, and it's going to be 10 meters per second squared downward. Now there's different ways to set up problems. In this video, I'm going to be very formal and use positives and negatives in the most traditional sense, where up is positive and down is negative. You may find ways to get around that as you're doing your problems, and as long as you can successfully sort of change that positive and negative, that's fine. But again, I'm going to show this in the most formal way. Taking a look at the information now, you should see that the second formula is going to be appropriate here. I'm not given any information about displacement or distance, and I'm not asked about it. So we'll use the second equation here. We can plug in the type of information that we know and then just do a nice calculation. And we do end up with a negative value, but that should make sense because the hammer is moving downward as it hits the ground. You don't have to state that it's going downward because the question just asks about speed. But at other times it's going to be really helpful to know that negative direction. Officially though, we can just say 4.5 meters per second is how fast it's going, what its speed is. Let's take another look, or a look at another question. So here an apple falls out of a tree. The tree has a certain height to it. So let's again take a look at the information that we're given in the problem. We can see that we're given a distance or a displacement. We'll call that our delta x. And we're asked to find a time. Again, there's some hidden information in this problem. The apple falls out of the tree. It's not thrown or kicked or launched. It just falls. And so that's an indication that the v sub 0 would again be 0. Our acceleration, because it's in the air during this problem, is going to be our negative 10 meters per second squared. Okay, so anytime an object is in the air, nothing is touching it during its motion, we're going to use this acceleration. Now at the very beginning, it's in the tree, but we are focusing on the process of it falling and hitting the ground. So in this case, now I'm involving a delta x. I'm involving a distance or a displacement. So we'll switch to the other formula. Again, our v sub 0 is 0, so that simplifies things a little bit here. Although it does look a little bit messy. Let's clean things up a little bit. Remember, you can use as little or as much algebra as needed to go to the final answer. So if you were able to sort of answer this sort of question just using your calculator, that's fine, but I'll show the steps here. I might simplify that 1/2 times negative 10 to give me negative 5, and then divide both sides by negative 5 first. Don't square root yet. You got to make sure that the t squared is by itself before you do that square rooting. And we would get about 1.7 as our answer. Okay, so it takes about 1.7 seconds for this apple to fall 15 meters. All right, we're just look at one more question here. This one is a little trickier, as we'll see here, but let's go through and sort of think through the same sorts of ideas. Think about what sorts of information is given, what we're asked to find. So here we are given an initial speed. It's not dropped or just released or falls. It's actually launched or kicked. I guess it's kicked here at a certain speed. So that's going to give us an initial speed of v sub 0. We are asked to find the time. All right, so how about some hidden information here? Again, once the girl has kicked the ball and it's no longer touching her foot, that's the part of the motion that we're kind of looking at here. At that point, the ball is in the air, only gravity is acting, and so we would be able to say that the acceleration is negative 10. Notice how here the signs are going to be really important because the speed of the ball, the velocity of the ball to start is upwards, positive, but the acceleration direction is negative, it's downward. So the signs, the plus and minus signs, are going to be very important in this problem. All right, so how do we take care of this problem? I don't really have a lot of information. It doesn't seem like there's enough to really determine this time. Well, there's going to be a little bit of a trick here, and there's actually three kind of typical ways that people approach this question, and I'm going to show all of them. You can decide which makes the most sense to you. So the main idea for all of them is that there's symmetry in this motion. When the ball goes up and then comes back down again, the motion sort of undoes itself. It slows down on the way up, and then it speeds up again in the exact opposite way on the way down. So one thing I can say is that the velocity is positive 25 meters per second when it leaves her foot, and when it comes back to the ground, it's going to be negative 25 meters per second. It's going to be that same speed again, but now going downward. And so I can use the v equals v sub 0 plus at equation and put in one velocity as positive and one as negative. And that will then determine how much time it takes to make that complete switch. It'll do it all together. It'll find the entire time, this equation will, for this all to happen. And if I go through my algebra, I would end up with 5 seconds for this entire motion. Another way I can think about it is I can sort of split the motion into two halves and say that at the peak, the velocity is going to be 0 for that little split second, right at that moment when it hits the peak, halfway through the motion. And that's the key thing. It's halfway through the motion. And so I'm going to find the time just to the peak by using 0 for this sort of like the final speed at the peak. So that's why I put that 0 in on the left-hand side of this equation. When I solve this, I actually only get 2.5 seconds. But I set this up so that it gave me the time to the peak. And so if I double that time, it'll get me the full 5 seconds. Again, different people think differently about this type of question. You just need to pick the method that makes the most sense to you. A third method also uses the symmetry of the motion, but recognizes that the ball starts at the ground, it goes up, and it comes back down again. And that means that even though it certainly moved through a distance, its displacement is 0. And that's actually what delta x means. Delta x is how far is the object gone compared to where it started. And so the third method actually uses the distance formula here and says that delta x would be 0, and still puts in the same sort of information, the initial velocity of 25, the acceleration of negative 10. Notice how in all the methods I'm still using that same initial information. To do the algebra here, though, we need to remember that this is a quadratic equation, and so a good method here is to factor out the t. Let me just do the algebra here. I'm going to first simplify a little bit, pull some terms together. So 25t minus 5t squared, 1/2 times negative 10 is minus 5. And then I'm going to factor out a t, and I get two terms giving me two possible answers. Either t is 0 or 25 minus 5t is 0. And that gives me an answer of 5 seconds. Some people like this method. Some people think the algebra is a little trickier for them. Again, you can pick which method makes the most sense for you. All right, quick summary then. Anytime an object is in the air with nothing touching it, the acceleration can be assumed to be officially 9.8 meters per second squared, but in our regular problem solving, we'll use 10. If we do a lab, we want to use 9.8 here, like we did in the past with the gravitational field strength. Now, when does this apply? Anytime an object only has gravity acting, where we'll ignore air resistance and nothing's touching it, then this is the force diagram, and we can use this value of acceleration. So something dropped, something thrown upwards. But as we'll see soon, it's also going to apply when something is pushed or launched either just straight across or at an angle. So it's going to be a very useful idea as we move forward in this unit.